All right, so today is the sixth day. Today we saw mainly two things, which was the how to initialize the weights of neural networks, and the second one is batch normalization. We delve a little bit into the papers, and we expand the previous explanation in order to implement the batch normalization. And yeah, about the initialization of the weights, we had two main problems. The first one was that if we had a softmax, the last layer there was a softmax, and in the first instance of the training, we had a big loss. The loss was really high. So this can be explained by the fact that if the model is very confident in giving a bad label, that means that it assigns a big probability to some output that shouldn't be, and this can happen at the first step of the training. Then the loss is going to be very very high, and then the convergence is going to be a little bit low because it starts from a big loss. So one way to fix it is by starting from a uniform and very close to zero weights. So what we do here is just basically multiply the weight and the bias by the initialization of the weight of the bias by some small number to make it close to zero, just for the first iteration. And secondly, we have the problem of the dead neurons or the vanishing gradients, and in which basically before applying a hyperbolic tangent to uh, the hidden layer, if the distribution, I didn't plot the distribution here, but if the distribution of the input is very skewed toward the tails, so that means that it's very either close to 1 or close to minus, like very high or very low, then the derivative, yeah, because the derivative it's gonna be 0, very close to 0. That's the graphic of the derivative of hyperbolic tangent. It's like this, so it either explodes. So yeah, so if it goes to 0, then it's a dead neuron. Once it's 0, the gradient, because in the way automatic differentiation work, it's because of the chain rule, you multiply by the gradient of the previous one. So if it's 0, then the neuron is dead and you cannot change it. So one way to fix it is to use other activation functions that don't have this problem, or also control the initialization, which we want initialization close to 0 in order to prevent like this extension towards this skewness. And we saw that there are specifically the paper of Javier Glorot and Glorot, in which they show which are the best scaling for this initialization. In this case, for tangent is 5/3 times the fanon, to the square root of this. This is, I believe, the number of parameters, the number of hidden layers, of hidden neurons the layer has. And that's it. And that's for initialization. Then we saw batch normalization. We saw a bit of the paper. And basically here, regarding batch normalization, the main interest is it provides training stability, because we don't start anymore. Yeah, it provides training and stability, but we have to apply also a little possibility of the distribution of each batch to change. That's why we add this bias, a bias and a gain. All right, and that's it. It's a really useful method, although it's not the only one. We're gonna implement more. And now the question becomes, how do we predict a single observation? If for the batch normalization, what we're doing in the batch normalization is here, what we do is basically at each batch we subtract the mean and divide by the standard deviation, and we have these two parameters that we adjust, all right, that we compute. but um, yeah, these parameters that they retain state with just. But what I'm saying here is that how, if we need this in order to predict, how do we actually gonna predict a single value if we don't have the mean and the standard deviation of a whole batch? And the answer is that we save this into two parameters, one which is like the exponential moving average, which is these two parameters, which use something called momentum. We initialize these parameters at 0. Here we do this, and then we make them take into account the average and the standard deviation of each batch in order to move around and to reflect this the nature of the training. And it's more dynamic than just using the mean and the standard deviation of the whole set. And as a side note, also in BatchNorm there is a epsilon added in the denominator here. Where is it? Here. There is an epsilon, but here, because the standard deviation here, I mean, if this is exactly 0, then you are dividing by 0. That's a problem. So with a small epsilon, you fix this problem, and that's it. And finally, also we remove the bias before batch here, because if we apply batch normalization, we are removing the mean. So in that sense, we are removing the bias, so the gradient it's gonna be 0 in this case, so there's no use, so we can remove it. And that's it.